Greetings, Chem 2 students. Mr. Keister here with you again today. This is the video for Wednesday, November 18th, 2020, which is our scheduled 63rd day of school for the fall semester. Always keep in mind, though, that the dates could change for a variety of reasons, but the lessons and the order that those lessons are presented will remain the same regardless. So let's take a look at our do nows and see what our schedule is for today. Today you are picking up Organic Compounds number 2 assignment, which is page 84. Yesterday we began Unit 5 over Organic Chemistry, a short unit on Organic Chemistry, and you picked up pages 81, 82, and 83 respectively. Homework. Your homework for today was to start the Organic Compounds number 1 assignment, numbers 1 and 2 only. Hang on to that. We will finish it up today and then begin our next assignment as well. If you want to check your answers, if you're here in class, of course, they are posted on the backboard. If you are at home, you may check the answer keys page on Canvas. So today we're going to continue on with the short version of Unit 5, which involves the nomenclature, of course, which is naming and formula writing, of organic compounds. Today we will finish up with the hydrocarbons, alkenes, and alkynes, and then we will get started with the nomenclature of alcohols. You'll finish your assignment from yesterday and then also begin today's assignment number 1 through 5 only. So finish the assignment we began yesterday, and then on the new assignment that you picked up today, page 84, just mark on there numbers 1, 2, 3, 4, and 5. We will get to those today. Please note, included in this unit is the memorization of the basic prefixes and types of structures that you will see most often in organic compounds. This information will be on the next several exams and most definitely on the first semester final exam. Remember yesterday I told you we're not going to have an exam over Unit 5 per se. It's quite short, but we were going to include that information on several future exams as well as the final. So keep that in mind. So having said all that, let's get to today's lesson. All right, so yesterday we looked at the prefixes that are used in organic chemistry, regardless of the compound. Those prefixes tell us the number of carbons in that particular organic structure. Remember, 1 carbon is meth, 2 eth, 3 prop, 4 but, 5 pent, 6 hex, 7 hept, 8 oct, 9 none, and 10 dec. And then we yesterday started our study of hydrocarbons, organic molecules that only contain hydrogen and carbon, respectively. And we looked at alkanes, which are the simplest type of hydrocarbon, whereby all carbon atoms are bonded via single covalent bonds, right? Alkanes. And again, their general formula is C to the N, H to the 2N plus 2, where N is the number of carbons in the alkane, and 2N plus 2 is the number of hydrogens. All right. We also looked at how to write a shortcut version of a Lewis structure, as well as a regular type formula that we use in equations only. All right. So having said all that, let's get to alkenes, shall we? So alkenes are hydrocarbons that contain one double covalent bond between 2 of the carbon atoms. All right, only one double covalent bond. The rest are singles. All right, the rest are singles. This is a type of unsaturated hydrocarbon. We talked about saturated. Alkanes are saturated in that each carbon atom has the maximum number of hydrogens attached to it that it possibly can. This is an unsaturated hydrocarbon because not all carbon atoms have 4 single bonds around them, and thus there are fewer hydrogen atoms in the compound. When you add 1 single bond, that's going to eliminate 2 hydrogen atoms from that molecule. And so alkenes then have the general formula H to the, or I should say C to the N, H to the 2N. So however many carbons there are double the number of hydrogens. All right. Now, bold-faced star must mean it's important, right? A number is used when necessary to designate which carbon atoms are double bonded. All right. the number is made as small as possible, whichever side you begin numbering from, and I will go over that with you in detail here in just a few minutes. All right? So, again, let's look at our little setup here. We have our inorganic formula, which is, again, our regular formula. This is the formula that we use in a chemical equation. The organic formula is basically shortcut of a Lewis structure, and we talked about that yesterday. So we're going to start with the first alkene, which is ethene. And already I'm hearing, wait a minute. I remember that there was methane yesterday, which is the simplest alkane, which has one carbon, CH4. Why in the world isn't there a methene up here on the board, Mr. Keister? Well, let's look back at what an alkene is. A hydrocarbon that contains one double bond between two of the carbon atoms. Well, you can't have a double bond between two carbon atoms unless you have two carbon atoms in the first place, right? So remember that. There is no such thing as methane, all right? The simplest alkene is ethene, all right? Again, ene ending means it's an alkene. And so ethene has two carbons in it, and then twice the number of hydrogens, of course, would make four. So its regular formula is C2H4, all right? So again, no methane, all right? No such thing. So let's look at ethene. So it's got two carbon atoms bonded together with a double bond, which is going to leave only two slots available for hydrogens. Each carbon, of course, follows the octet rule. And so if we were looking at its full-blown Lewis structure, it would look like this. Don't forget Vesper. Those single bonds of the hydrogens repel each other. So your structure basically looks like that. All right, now here's the shortcut version of that, the organic formula, the shortcut Lewis structure. So again, we have a CH2 here and a CH2 with a double bond between the C's. And so we write it like this, CH2, double bond, CH2. All right? Again, that double bond is not between the C and those two H's. That's not what it means. That double bond is between the two carbon atoms. All right? Okay, let's go to the next page. So our next alkene is propene. All right, so propene has three carbon atoms in it. So let's go write that down. All right, so we have, I'll put one up here. So let's say C, 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 and one of those is double bonded. So if I put the double bond between, I could put the double bond between the first two carbons, right? Or I could put the double bond between the middle and the last carbon. All right, so let's take a look at that. Now, I mentioned earlier that we can number the carbons from either direction. You know, we humans are very accustomed to numbering, at least in the United States, not sure about all other countries, but numbering from left to right. All right, so if I number these carbons, 1, 2, 3, then the double bond would be between carbons 1 and 2. All right, but if I number them right to left, which there's no law saying you can't, all right, in organic chemistry anyway, then I number from the right to left, then over here it'd be 1, 2, 3, and the double bond will be between carbons 2 and 3. The rule is, however you number, and it doesn't matter, you have to use the lowest numbers possible. So in this case, numbering from left to right, the double bond is between carbons 1 and 2 rather than 2 and 3. But if I draw it the other way and number from left to right, the double bond is between carbons 2 and 3. However, if I number right to left, 1, 2, 3, the double bond is between carbons 1 and 2. Again, the lowest possible numbers there are carbon 1 and 2. So regardless, if you draw it with the double bond here or the double bond here, it's still between carbons 1 and 2. That being the case, we do not need a number in this formula's name. It's not necessary, all right? So let's go ahead and finish off one of these. The first let's do the upper one here with the double bonds on the left side. So based on that, the first carbon would require 2 hydrogens to complete that carbon's octet. Look at the middle carbon. It's already got 3 bonds around it, which means it's only going to take 1 hydrogen. So just 1. And then on the right side, we would need 3 carbons. So let's say based on that, its organic structure, its shortcut Lewis would be CH2, double, CH, single, CH3. Now, if I wrote it the other way, which is perfectly acceptable, all right, I'll put an or there. It would look like CH3, single, CH, double, CH2. A mirror image of the one we just drew. And again, it doesn't matter how you draw it. The double bond, based on our numbering system rules, would be between carbons 1 and 2, no matter how you draw it. So either one is okay. All right, either one is acceptable. So however you decide to do it. Again, I always naturally number from left to right, and that's the way I'm going to do it, but it doesn't really matter. All right, so let's look at the next one. C4H8 which would be called what? Well, C4 is bute, so it'd be butene. All right, butene. Now I got a couple of stars here. Must mean something, and let's put a little note beside there. Number needed here. Number needed in name, and I'll explain, and we'll see why here in just a second. So 4 carbons, 1, 2, 3, 4. If I put the double bond between carbons 1 and 2, or put it over here between the last 2, that would still be carbons 1 and 2 if I numbered right to left. So either way, or reversed. And let's finish off the hydrogen. So we need 2 there, 1 there, 2 there, and 3 there. Either this way or reversed, the double bond is found between carbons 1 and 2. When that is the case and you name it, you use the lower of those 2 numbers. So that would be a 1. So this structure here, so which would be CH2, double, CH, single, CH2, single, CH3, would be called 1-butene. Again, you use the lower of the 2 numbers where the double bond is found, which in this case is carbon number 1, followed by a dash, and then the name butene. However, now we have another possibility. If I put my 4 carbons here, and I put that double bond in the center, all right, which is another possibility. If I number left to right, that double bond is between carbons 2 and 3. If I number right to left, that double bond is still between carbons 2 and 3. All right, this is not the same as the previous one. All right, so let's draw that one. So it'd be, let's see, we need 3 hydrogens on that first carbon on the left side, 1 on the second, 1 on the third, and 3 on the fourth. So this would be CH3, single, CH, double, CH, single, CH3. And now, with that double bond there, again, regardless if you number left to right or right to left, it's between carbons 2 and 3. We use the lower of those 2 numbers. This would be called 2-butene. So we have 2 possibilities. These are called, and you need to know this term, structural isomers. Isomers. Iso meaning the same, all right? Structural isomers. These 2 are structural isomers, okay? Now, what does that mean? Well, what it means is, in regards to, they're both butene, all right? They're both butene. However, their properties, based on the location of that double bond, which then is going to affect their shape slightly, all right? Because of that, the repelling forces are found in a little different location, all right? which is going to affect their properties ever so slightly. So their melting points, boiling points, densities, etc., are slightly different. Now, when you look up the boiling point of butene, for example, you're going to get one number, all right? And usually there's a little notation there that says that is the average boiling point of butene, meaning if you take into account both isomers of butene, the boiling point average between those two is the one that would be recorded. All right, they're very, very close. All right, they're very, very close. Structural isomers. Remember that name. All right, so next, alkynes. All right, alkynes. Takes all kinds, right? Good organic joke there. Well, maybe not that good. Alkynes are hydrocarbons that contain one triple bond between two of the carbon atoms. All right? So now we're adding a triple bond, or we're throwing in a triple bond rather than all singles as in an alkane. What that's going to do is change the number of hydrogens. Now, from an alkane, it's going to reduce it by 4. So alkynes have the general formula C to the N, H to the 2N minus 2. All right? Minus 2. As in, little note here, as in alkenes, a number is used when necessary to designate which carbon atoms are triple bonded. Again, the number is made as small as possible, whichever side you begin numbering from, left to right or right to left. All right. Again, I always number left to right. That's just natural for me. And so, but of course, that means that there are other options for you as well. So let's look at those. Raise the screen up here. Okay, so our first alkyne listed is ethyne. All right, so here again, there is no methine. It's our regular formula over here. Okay, a little star there, no methine. There's a methane, excuse me, but there's no methane and there's no methine either, because you got to have a minimum of 2 carbons to have a triple bond between them. And so the first alkyne is ethyne. So now think about it. We now have ethane, we have ethene, and we have ethyne, and they are all 3 different compounds. All right. So our first alkyne again is ethyne, C2H2, 2 carbons. Twice that number of hydrogens minus 2. So that would be 2, C2H2. All right, so 2 carbons, triple bond, which means each carbon then is only going to be able to handle, as you can see, 1 hydrogen in order for each carbon to complete its octet. And so its organic formula, which is again a shortcut of a Lewis structure, would be CH, triple bond, CH, all right? And again, you don't need a number here, because if you number left to right or right to left, the triple bond is still between carbons 1 and 2. So if it's the same, then there's no need for a number, okay? So let's look at the next one, C3H4, propyne, all right? So we got 3 C's. So if we put the triple bond on the left side between those first 2, it would be there, or if we do it on the other side, it would be there. But again, if you number left to right here, it's between 1 and 2. Right to left is 2 to 3. Winner, 1 and 2. If you do it this other way, if you number left to right, the triple bond is between numbers 2 and 3. If you number it right to left, it's between 1 and 2. Winner, 1 and 2 again. So it's 1 and 2 either way. Don't need a number for this one either. All right. It would be 1 propyne regardless. But if you don't need it, we don't use it. All right. So pick whichever one you want. I'll use this top one here, the first one. So we're going to need a single hydrogen on that first carbon. None on the middle one. Its octet has already been achieved already. And then 3 on the one on the right, which would then give us an organic formula of CH triple C single CH3. And again, I'll just write out here to the side or reversed. You could have drawn it the other way as well, and that would be perfectly correct. All right. And then let's go to the next page. Got a double star next to C4H6 which would be butane. Must mean we need a number. All right. Well, of course we do. For the same reason we needed a number with butene, we're going to need a number with butane. All right. So we can go. So we got 4 carbons. 1, 2, 3, 4. Could put a triple there between the first 2, or if we put a triple on between the last 2, it'd still be a triple between carbons 1 and 2, or however you look at it. So either way, or reverse. And if we finish that off with hydrogens, let's see, it'd be 1, none, 2, and 3. So that would be CH, triple, C, single, CH2, single, CH3, or reversed. That would be, the triple bond would be between carbons 1 and 2. That would be 1-butane. 1-butane. But there is an isomer, all right? There's one here because, or could put that triple bond between the 2 middle carbons. Either way you go, left to right or right to left, that triple bond would be found between carbons 2 and 3. Again, we use the lower of the 2 numbers, which would be 2. And so this would be 2-butane. As we fill in the hydrogens, let's look like 3, none, and 3. So we would have CH3, single, C, triple, C, single, CH3. This would be called 2-butane. Again, these are structural isomers. They contain the exact same number of carbons, the exact same number of hydrogens, the exact same number of triple bonds, which is 1, all right, and the exact same number of single bonds, which is 2. So these, and again, their properties are very, very similar, but they are not exactly the same because of the location of that triple bond. All right, so again, we have 2 structural isomers here. So that takes care of alkenes and alkynes. So we have 3 hydrocarbons we've looked at. Alkanes, all single bonds between carbons. Alkenes, 1 double. Alkynes, 1 triple. And again, once you get to a certain number of carbons in an alkene or an alkyne, you're going to need a number in its name because of the existence of structural isomers. Okay, last one for today. Now we're going to look at alcohols. All right, alcohols. An alcohol contains a hydroxyl group, which is an OH group. Now I know you say, wait a minute, OH, that sounds familiar. Oh, hydroxide ion. Yeah, well, that's OH minus 1. All right. A hydroxyl group is very much related to OH minus 1, except there's an electron missing. All right. And so it looks like this. OH. All right. There's a single unpaired electron on this O here. Remember, O has 6 around it. And that then is where the single bond attaches on to the main chain of carbon atoms. All right. A hydroxyl group replaces a hydrogen atom in an alkane. So an alcohol is formed from an alkane, all right, where one of the hydrogens is dropped off and an OH is attached to it, all right. So a hydroxyl group is an add-on. It's not a standalone molecule, all right? It's not a standalone molecule. It's an add-on. It's an attachment. It attaches to a carbon atom in an alkane, all right? Remember that. And again, a number is used when necessary to designate which carbon atom the hydroxyl group has attached itself to. And again, the number is made as small as possible, regardless of if you number your carbon atoms left to right or right to left. All right. So let's raise up the screen here and talk about the alcohols. So keep them straight. Hydroxyl group and hydroxide. Very much related, but not the same. Hydroxide is an ion. A hydroxyl group is an attachment to an alkene. Okay? All right, so we're going to compare alkene and alcohol because that's where alcohols come from, which is an alkene. All right, so here's methane, CH4. Remember, it looks like that. Okay, 4 hydrogens attached. Methanol, which is the simplest alcohol, it's the 1-carbon alcohol. We start with the same thing here, but now one of those hydrogens is replaced with a hydroxyl group. All right, and it doesn't matter which hydrogen you replace; they're only attached to the same carbon. All right, so what do we have for our organic formula? Well, it would be CH3 single O. Don't forget those 2 unshared pairs of electrons around that O, and then the H. So this would be CH3OH, which is methanol. Now, your regular formula that you would use in a chemical equation would, of course, eliminate the bonds and the dots from that abbreviated Lewis structure. It would just look like CH3OH. Okay, so ethane, our alkane, again has 2 carbons, 6 hydrogens around it. Remember, carbons are single bonded. So ethanol, which I'm sure you've heard of. I mean, we use ethanol mainly now as an additive to gasoline or as a standalone fuel. We have cars, they're called flex fuel cars or SUVs or trucks that can run purely on ethanol. You can buy ethanol now at most gas stations. And if you don't use pure ethanol as a fuel then the regular gasoline you buy now contains ethanol as an additive as well. So anyway, we're going to replace one of those hydrogens with a hydroxyl group, an OH group. And again, it doesn't matter if you replace it on this right carbon or on the left carbon. Either way, it's on the first carbon. If you're numbering right to left or left to right, either way, it's on the first carbon. So we're not going to need a number here. No number needed with ethanol. And so our organic structure would look like this: CH3 single, CH2 single O, 2 pairs of dots, don't forget those, H, CH3, CH2, OH. Now, the regular formula that we use in our chemical equation would look like this: C2H5OH, where we combine these C's and these H's, but we leave the OH separate because that's bonded to this carbon separately from the other thing. So it would look like that, C2H5OH. That is also ethanol, as you would write it in an equation, but the shortcut Lewis structure looks like that, the organic structure, CH3, CH2OH. Of course, the full Lewis structure would be like this, with those hydrogens on there. All right, so no number needed there. Okay, so here's the 3-carbon alcohol, C3H7OH, which would be called propanol. All right, propanol. Now, I got stars there. Uh-oh. Must mean we need a number. Geez, on alkenes and alkynes, we didn't need a number till we got to 4 carbons. Not true with alcohols, though. Let's take a look why. All right, so 3 carbons, all single bonds, all right, because remember, alcohols formed from alkanes. Okay, so let's see where we can put that hydroxyl group. Well, if I put it on either end, if I put it on the right end or the left end, again, based on our ability to number from either side, it would be on carbon number 1, all right? These would then fill in with hydrogens. And I'll put or reverse, as we could put that OH on the far left side. Either way, again, it's on the first carbon. But we now have another possibility. Or CCC, we could put that OH on the center carbon. I'm going to go up there, or I could go down, of course. Either way, they're just mirror images of each other. And we put our hydrogens in here, 3, 1, and 3. And now the hydroxyl group is on the second carbon. That's a different isomer. All right, here's why we need it. So then here's why we need the number. So it would look like this. First choice, CH3, single CH2, single CH2, single O, 2 dots, set the dots, OH. That would be 1 propanol. And the other possibility then would be CH3, CH. There's an H still attached to that middle one. And then coming off of that C would be again O, 2 sets of dots, H. You could go down or up, either way. I did down here because I don't have room to go up. So either way is fine though. Single CH3. This would be 2 propanol. 2 propanol. So we have isomers now with only 3 carbons. All right. Since we can place that hydroxyl group, that alcohol group, in 2 different places. And again, the properties of propanol, as you would look them up, probably have a little asterisk next to it. Those are the average of its 2 isomers properties. All right. And then let's do the next one, C4H9OH, which I hope by now you would see that is butanol. Butanol. And going to need a number there too. We needed a number with 3 carbons. We're certainly going to need one with 4. All right, so 1, 2, 3, 4. So I put that hydroxyl group on either end. 1, 2, 3, 4, or 1, 2, 3, 4. It's on number 1. Or if I put it on this end, it'd be 1, 2, 3, 4, 1, 2, 3, 4. It would still be number 1. All right. So this would be C. Let's see, 3 hydrogens there. 2, 2, 2. Yes. So it'd be CH3, single CH2, single CH2, single CH2, single OH, or reversed. That would be 1 butanol. 1 butanol. All right. And then we could also put that OH on either the second carbon from the left or the second carbon from the right. And again, depending on how you number, it's going to be between carbons 2 and 3 either way. The lower the 2 numbers, 2 is the winner. So it would be 2 butanol. 2 butanol, either way you look at it. So let's see, 3 carbons there. 1, 2, 3. So this would look like CH3, CH with an O coming off of that C. And then, of course, the H. And don't forget the 2 sets of dots around the O. And then CH2, CH3 again, or reversed. We could put that OH right here on the second carbon from the right, just as easily as we could the second carbon from the left. Either way, they are found between carbons 2 and 3. 2 is the winner. The name would be 2-butanol. 2-butanol. Isomers there. So beginning with 3 carbons in an alcohol and then going on through 4 and more, 4 and beyond, you're going to need a number, all right, as part of the name. Okay, well, I think that takes care of today's lesson. So again, your assignment is to finish the assignment that you began yesterday, and then also on the assignment you picked up today, numbers 1, 2, 3, 4, and 5 only. All right. So we finished up hydrocarbons today, and then we began with alcohols. We're going to be looking at several other organic compounds that contain other attachments. Again, the OH group, the hydroxyl group, is an attachment. It's called a functional group, by the way. And we're going to look at other functional groups which lead to other types of organic molecules here in the next couple of days. So until next time, this is Mr. Keister signing off. Take care, everyone. Stay safe, stay focused, and keep working hard. And until next time. We'll see you.